I will present our project about the analysis of the water distribution system at Female Hostel Block B at Polytechnic Kuching, Sarawak. The purpose of this project is to analyze the water distribution system at the selected study area and evaluate its efficiency in supplying adequate water to users. This study focused on the identifying the system components, flow arrangement, and overall performance of the distribution network. The selected location is at Female Hostel Block B at Polytechnic Kuching, Sarawak. This location was chosen because it represents a residential building with a centralized water supply system that can be analyzed in detail. The scope of this study includes the assessment of the water supply system, such as the type of system used, storage facilities, pipeline distributions, and control components involved in delivering water to users. Next, I will move to the background of study area. Block B is a part of the campus development, which was built in phases to accommodate the increasing number of students. In terms of function, Block B serves as a female student hostel, providing basic facilities such as bedrooms, rooms, and a water supply system and a drainage system. The water supply system in building uses a pump system that distributes water from a ground tank to the entire building through the pipelines. Next, I will explain about the function of all the components at Block B. The water distribution system consists of several important components. The storage tank acts as the main source of water and ensures continuous supply. The pump increases water pressure so that water can reach the upper floors. The main pipe carries water from the source to the different parts of the building, while branch pipes distribute water to the individual rooms and fixtures. Valves are used to control the flow of the water and allow maintenance work. Finally, outlets such as taps and toilets are the points where water is used by the users. Next is water distribution system descriptions. Water distribution system used in this building is a pump distribution system, where water is delivered using a pump because gravity alone is not sufficient to supply water to the upper floor. Next is water storage. Water is first stored in an external HDPE ground tank, also known as the blue tank, which is located at the ground level. This tank is the main storage and ensure a continuous water supply. Gate valves are installed on each floor to control or stop the water flow during maintenance or in case of leakage. The system operates as a single pressure zone where one pump controls the pressure of the entire building. However, pressure-reducing valve PRVs may be installed at the lower floors to reduce excessive water pressure and ensure a balanced distribution throughout the building. Based on the analysis, the system does not fully apply the DMA concept because there are no flow meters or monitoring devices. However, a basic zoning concept can be observed. Each floor can be considered as a zone since isolation valves are installed at every level. In conclusion, the system uses a simple zoning approach but not a complete DMA system. However, it has potential to be improved in the future. That's all from me. Thank you.
Moving on to a critical aspect of our analysis, which is the leakage risk factor. Identifying this factor is essential for ensuring the long-term integrity of the water distribution system and preventing non-venue water loss. We have categorized this risk into 5 primary areas, which is pressure, age, corrosion, soil conditions, and workmanship. First, we look at pressure issues, which are particularly significant in high-rise structure. For example, water hammer. Sudden change in flow can create surge pressure that stresses piping joint, particularly the blue piping joint seen in our system. And static pressure. High head pressure from the vertical layout can lead to creeping leaks in fixtures over time, making consistent pressure management vital. Next is pipe age and fatigue. As infrastructure reaches the end of its design life, it's become brittle. This brittleness leads to longitudinal crack. Furthermore, vibration stress from pump operations or environmental factors can accelerate material fatigue, significantly shortening the lifespans of the pipe. The central risk factor is corrosion, which we can see in two forms, which first is atmospheric oxidation. This typically affects the exterior isolation rust on flank bolts valve system. Second is pitting. This is localized damage that can penetrate blue coating, leading to pinhole leaks that are often difficult to detect until they become major failure. From the geotechnical perspective, soil conditions play a major role in underground pipe stability. Differential settlement soft soil can cause shifting, which puts immense strains on buried lines. Shear stress movement, specifically at tank entry connection, can create enough shear force to snap pipes at their most rigid point. Finally, we must account for workmanship and installation's quality. For jointing failure, misaligned gaskets often fail when subject to high pump pressure. And for structure support, a lack of proper bracing or support can cause heavy valves to sag, leading to thread leaks and eventually connection failure. By understanding this variable, we can implement better preventive maintenance and design more resilient infrastructure to mitigate this leakage risk.
Hello, my name is Shaira Aini binti Aju, and I will continue this presentation by discussing how we actually find and measure leaks. In my report, I evaluated 5 different approaches, including reservoir monitoring, delivery pipe testing, and the gas tracer method. However, for Block B, I have selected a combination of minimum net flow and sounding inspection as our primary strategy. Our first step is minimum net flow. We monitor the main water meter between 2 am and 4 am, which is when student activity is at its lowest. If the meter continues to speed at a constant rate during this hour, it confirms a background leak or a burst pipe, because there is no legitimate reason for a water to be flowing. We choose this because it is extremely cost-effective. It requires no special equipment other than the meter we already have, and it gives us a clear answer, yes or no, on whether a leak exists. Once the monitoring net flow data confirms a leak, we use sounding inspection to find it. Our technician use listening stick or electronic microphone on valve and taps to hear high frequency vibration. I selected this over the gas tracer method because it is especially effective for concrete buildings like our hostels. Since most of our leaks happen in wet blocks like toilets, sounding can pinpoint the exact roof or wall. This means we don't have to break any tiles or perform destructive hacking just to find the pipe. To summarize, we choose this combined method for 3 main reasons. The first one is cost effectiveness. We use existing infrastructure without needing expensive specialized gases or sensors. And the second one is high accuracy. It is highly effective for residential setting, pinpointing leaks behind brick walls and underfloor slab. And the last one is non-destructive. Unlike delivery pipe testing, which requires isolating the whole system, these methods can be done without interrupting the water supply for students during their busy morning or evening hours. Next, I will continue by presenting our leakage control proposal to improve the water distribution system for Block B at Polytechnic Kuching Sarawak. My presentation focuses on 4 key areas, which are leakage reduction, valve zoning, NRW management, and smart monitoring. First, I will explain our leakage reduction measures. Currently, our old metal pipes are prone to rusting and small pinhole leaks. I propose replacing these with HDPE or ABS pipes. These modern materials do not rust and are flexible enough to handle the vibration from our water pumps. I also suggest installing pressure reducing valve on the lower floors. Without this, the high pressure needed to push water to the top floor can cause silent leaks in the ground floor toilets. This step will physically strengthen our system and stop water waste. Next, let's look at valve placement and zoning. In many of the systems, you have to shut down water for the entire building just to fix one leaking tap. My plan is to install isolation gate valve at the entrance of every floor. This divides the building into 6 independent zones. If a pipe breaks on level 1, we only need to turn off the water for that floor. The students on the other 5 levels can continue their daily routines without interruption. This makes our maintenance much more efficient and student-friendly. Moving on, I will discuss how to reduce non-revenue water or NRW. NRW is essentially water that is produced but lost before it reaches the user, often due to hidden leaks. I propose turning Block B into a district meter area. This means we treat the block as its own secret zone. By measuring exactly how much water enters the block and comparing it to the number of students living there, we can pinpoint exactly how much water is being lost. This helps the maintenance team find invisible problems much faster. Finally, I am proposing smart monitoring method. Instead of using old-fashioned manual meters, we should install IoT-enabled smart meters. These meters provide digital data in real time. The most important feature is night flow monitoring. Between 2 and 4 a.m., when most students are asleep, water usage should be near zero. If the smart meter detects constant flow during these hours, it sends an automatic alert to the maintenance team. This allows us to fix leaks immediately instead of waiting days or weeks to notice them. That's all from me. Thank you.
To wrap up our analysis, the finding lead us to one clear conclusion, which transitioning to a monitor and zone network is no longer just an option, but a necessity. By implementing a zone system, we can drastically reduce water waste by detecting and isolating leaks before they become major failures. Beyond just saving water, this approach is vital for protecting the long-term structure integrity of our campus infrastructure. Consistent monitoring prevents the soil erosions and foundation issues that often follow undetected underground leaks. Ultimately, moving toward a smarter, more controlled distribution network ensures that our facility remains sustainable, safe, and cost-effective for years to come.